There are many topics that could not be covered in the course on distributed algorithms. We mention here two important topics. We just said that a process may fail by just crashing and stopping execution. The algorithms presented in this course assume this mode of failure. However, there are other types of failure that we will discuss briefly in this unit. Byzantine process failure and corresponding algorithms, and transient failure and self-stabilizing algorithms. What is Byzantine faults? Some processes might behave arbitrarily, for example, sending wrong information, omitting messages, or just not adhering to the protocol of the algorithms. Byzantine algorithms that tolerate this kind of failure only tolerate less than 1/3 Byzantine processes. Non-Byzantine algorithms can often tolerate less than half of the nodes failing in the asynchronous model. Self-stabilizing algorithm is the other topic that we will not discuss. These are robust algorithms that run forever, but the system might exhibit temporary failure. For example, it can be temporarily incorrect and exhibit transient failure. These algorithms revert to correct behavior once the transit error disappears. That is to say, the system eventually becomes correct. Self-stabilizing algorithms have two properties. They can either be in a legitimate state or in illegitimate state. However, an algorithm is self-stabilizing if it exhibits the following two properties: convergence and closure. Convergence means that given any legitimate state, the system will eventually go to a legitimate state. And closure means that if you are in a legitimate state, you stay and remain in the legitimate state. So that's what we said about a self-stabilizing algorithm. And we can look to it this way. So this is the whole state space of the system. State space. And this part, the light blue, is the illegitimate state. And this part is the legitimate state of the system. A process, or the system as a whole, is some illegitimate state. It will move to the legitimate state, that is convergence, and it will stay in the legitimate state, that is closure. A lot of advantage of self-stabilizing algorithms. They are robust to transient failure, and they don't need initialization because they can start from any state and move to a legal legitimate state. And in fact, they can also be easily composed. You can have two services. Each of them is a self-stabilizing service. If you put them together, compose them together, you get one service that is self-stabilizing. So a service composed of two self-stabilizing services is also self-stabilizing service. Here is an example of a self-stabilizing algorithm. It is called the token ring algorithm. So we wish to have one token circulating among a set of processes. And this token represents a resource that only one process can have at a time. But sometimes error can occur. An error will lead to two or more tokens circulating. Eventually, we want to ensure that there's only one token. So as you can see, in the end, even after many tokens circulating, we have only one token. This is the end of the first introduction lecture. What we are going to do now is to look to the content of the course.